Transactions are non-trivial. If you try to implement them yourself from scratch, it's hard. If you try to implement them on a database that doesn't support it, you're going to run into a lot of complexities. If you operate on the assumption that your database has them, but in reality it doesn't meet the standard, you could be losing data without even knowing it. With the expansion of IoT data and time series modeling, there is a critical need for a database to offer ACID data consistency without sacrificing your performance, especially as your data scales exponentially. What exactly makes a document database fully transactional? Do MongoDB and RavenDB pass the smell test, or do they endanger your data? In this webinar, Microsoft MVP Oren Aney discusses what a database must prove to be worthy of the coveted, fully transactional badge of honor. He will discuss the challenges presented in the Jepsen article of May 15th and explain how each database answers them. You will discover what is required of you to enable ACID for each database, how to maintain your performance while keeping ACID, how to reduce the complexity of ACID at scale, which database offers valid snapshot isolation as part of their ACID promises, the wealth of knowledge and efficiencies a NoSQL document database can accumulate over a decade of keeping ACID. Feel free to ask questions by clicking the Q&A button at the bottom of your screen, and Oren will be happy to answer them throughout the session. Enjoy your presentation, and here's Oren.
Hi everyone, thank you for showing up for this webinar. I want to talk about ACID, and I try to find good pictures of ACID online, and I mostly regret that. The simple issue is that ACID stands at the core of how you build a proper database. How you treat the ACID properties is incredibly important. So let's start from the beginning. Let's talk about what ACID is. And ACID stands for atomic, consistent, isolated, and durable. And you can see it on the screen what exactly this means. And the whole idea is quite simple. I want to put data somewhere, and I want it to be safe. Now, what does it mean I want it to be safe? Safe for what? I want to be safe from concurrent transactions. So I want every transaction to be able to work on the data as if it was independent. That if there is another transaction going on, I don't want it to be stepping on my toes. This is isolation. For consistency, I want to have my records valid. There's really, this is a really ill-defined term, because what consistency means is very much application dependent. But the core of this is simple. Based on my business rules, based on how I think about the data in the database should be valid. And the database should help make sure this is the case. Now, then we get to atomicity. And atomicity is really interesting. Atomicity says something very simple. When I commit a transaction, all changes that happen within this transaction should go in or should not be there at all. I don't want to be stuck in some halfway state where some of the changes made it in, but some don't. The error conditions that I have to deal with are crazy enough as it is. And finally, we have the notion of durability. Durability means something very simple. If the database told you that it's going to keep your data, you hold it to its word. Which means that if 1 millisecond after your data has been committed, you pull the plug, then the data needs to be safe. The data needs to be durable in a persistent medium. For distributed databases, there are additional concerns. For example, if you're using RavenDB in a multi-node cluster, you can actually go into any single node in the system and make a write. With Mongo, you can only go to the primary node. So how do you maintain transaction consistency in a distributed environment? That's something that we have to make sure that we do properly. And it's hard. Also hard to remember to shut down Skype before you start a webinar. So let's talk about first, what is the quintessential example for transactions? Bank transfers. I want to move money from point A to point B, and I want to make sure that there is no money left on the floor. It's okay to fail the transfer. It's not okay for money to be deducted from my account and not show in the other account. It's not okay for money to show up from thin air. So that's something that we have to take into account. Funnily enough, I know of no real banking system that actually use transaction for that. And the reason they don't use transactions for that is that they can't. If you think about how it works for something like wire transfer, if I'm transferring money between two accounts on the same branch of the same bank, maybe we can do an actual transaction and just shift bits around in the same computer. In practice, however, we're going to have to do a much more involved process. We're going to take the money of one account, put it in a holding account, then send it to another branch or another bank entirely. It may go through international wire transfer options. None of this is transactional. And if you think that this can cause errors, you're correct. And trying to find out where the money went is the regular course for anyone who deals with wire transfer, especially international wire transfers. So this is the great example, just not a realistic one. So let's talk about transactions in RavenDB. RavenDB from day one, from I think 2008, 2007, when I first spiked the what eventually became RavenDB, had transactions. To be fair, I was aware that there are other data storage solutions, I actually don't call them databases, that store data but didn't offer transactions, but I could not grasp my head why you would ever want to do something like that. So transactions has always been part of the design of RavenDB. And by transaction, I mean that you had full ACID, atomic, consistent, isolated, durable properties on making a change to a document or to multiple documents in multiple collections. I think that to be able to do cross-node transactions, which is now what we call cluster-wide transactions, is something that shipped in 2.0. So call it 2012. And that has been just the way it is. RavenDB has been crash consistent by design and mostly by implementation as well. And you can see there is the Jepsen test that we wrote to test RavenDB itself, and everything works. That's how it should be. Now let's talk about Mongo. Mongo's first public release didn't have almost any of the ACID properties. Now I'm talking about 2008, I think. So that's way down the future, that's way down the past. But you can see the journey that they took. And there are, if you try to search for MongoDB transactions, you can see it took them a decade to get transactions. And along the way, there have been several Jepsen tests to check how things are going. And you will notice a theme. It took them a while to move from possible data corruption to just data loss. And again here, and in 2018, They have multi-document transactions, and just a month ago, less than a month ago, Kyle from Jepsen had issued a report, and he tested the distributed properties and the transactional properties of MongoDB and find that they're not good. We'll leave that at that. I have some choice code afterward, and we can talk about exactly what this is the case when we get to that. Now, I've been looking at Mongo for a while, and I got to admit, I'm trying to figure out a nice way of saying it, but I just can't. It's unimaginable to me that you have a database that doesn't keep data. And MongoDB, in pretty much every single point in time, have almost always preferred to go with speed over safety. Now, to be fair, this guy is a nerd. This guy is driving a red car. Probably most people want to be here. And speed is always wonderful to have. I mean, if you look at RavenDB benchmark number, then you can see we are really excited about those numbers. But we are excited about those numbers without sacrificing safety. Now, I can't give you a benchmark that says, oh, RavenDB is X safe. But that's because this is a binary property. It's either a yes or a no. Now, just to give you some ideas about the kind of choices that I'm talking about, MongoDB used to run in a mode that is called fire and forget. So you have a command, you send it over the wire, and then you say you're completed. At this point, the command haven't even left the user space buffer and hit the kernel, much less left the machine. It's going to be really, really fast. But if you have hiccups along the way, that's going to kill you, or that's going to cause you to lose some data. Even today, a lot of the defaults that Mongo has are about making things fast rather than making things safe. Now, the reason MongoDB exists, it wasn't supposed to be a product, it was supposed to be part of something larger, was to manage analytics on large amounts of log data. And in those scenarios, it makes sense to, well, we lose some data. We have so much of it, no one will notice. We're working in aggregates anyway. But this is used as a real database. And there are still cases where this still impacts design today. So let's look at the docs. I took it from the MongoDB docs today, and it talks about multi-document transaction called greater performance cost, blah, 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 blah. Oh, we have this feature, please don't use it. I will translate from marketing speak. So that's really interesting. It's really interesting because this is when you're actually starting to talk about what's going on behind the scenes. And let's talk about the Jepsen report from last month. Here are some of the issues that were found out. The default consistency level are set to local, which means that if you have multiple nodes running at the same time, we're going to read whatever the node that we hit is going to give us. That's going to be far less consistent. If we're writing to a single node and not waiting for it to get to the majority. Again, by the way, this is something that RavenDB does as well. But we don't have this issue of, oh, we have a single primary model. RavenDB by design has a multi-node setup where you can read and write from any node at the same time. For fun, if you set those values and then use transactions, they are ignored. You have to set them on yourself. And there's been some user studies about Mongo, and you see something really, really interesting. A huge amount of the people who use Mongo are using the default values. And those values matter. They matter quite a lot. Why is that? Because if you choose the bad values, you're absolutely going to get some great numbers in benchmark reports. But then you're going to be hitting those issues in production. And then there is this classic response, oh, you should have read the docs and used the appropriate configuration. And if it is a 1 or 2 person, that's okay. If it's 99.6% of users, that's not okay. Mongo used to ship with let's bind to all interfaces with no password and see how it goes. And then people realize that, oh, there is a lot of Mongo instances up there open to the public internet with no password. And even today, if you run a Mongo, it will only bind to localhost. Okay, perfect. That's what you expect it to do. But then you push it to production and you say, okay, what's the next stage? Oh, it doesn't work because it doesn't work on, I can connect it from remote. So I search, MongoDB can't run remote. And the first result on Google says, oh, let's go and change the listen URI to 0000, and you're back where you're at. RavenDB will flat out refuse to run in this case and will give you a scary warning. Hey, you're running in unsecure mode. And again, I'm just giving you some of the details that I found particularly irritating to see over and over. Now, here's some quotes from this, and you can see that Mongo does not violate strongest level, blah, blah, blah. The other issues is that this is if you have read the documentation, understood that, and went for the highest level options. If you use the defaults, and as we saw, a lot of people do use the defaults. The dirty reads, lost writes, and lots of fun in general. And we're talking right now about specific types of failures. Jepsen is mostly interested in distributed system architecture. But there is also something called fsyne. Now, fsyne is a really expensive command that database authors hate. Why is that? IO is slow, like super slow. But what's the problem with that? I want my system to be fast, so I can't actually deal with the IO. So there's a whole lot of buffering going on at multiple levels. And at some point, I accept a write in my database. And in order to make sure that this is durable, I have to write it to disk. And then I have to make sure that it is actually sitting in persistent media. And in order to do that, there are a few ways of doing that, but one of the most common one is fsyne. So RavenDB from the get-go says, okay, that's the price of doing business. We have to use fsyne. We have to make sure that the data is safe. Mongo took, I think, something like 5 or 6 years to actually get to the point where they even had the option. And even today, I literally went today and looked at I looked at the documentation and says, oh, by default, we're going to call fsyne every 100 milliseconds. And my response to that was, are you kidding me? Because I have to write to fsyne every single time I write. And I'm competing against you and you write once every 100 seconds. That's ridiculous. Here's my reaction. And by the way, just to understand, RavenDB tends to perform actually faster. equivalent or faster in some cases, especially for reads. But for writes, we're doing about the same as Mongo. But we're doing that with full ASCII consistency. And here is a picture of flowers. And why do I have a picture of flowers here? Because again, I really annoyed by the fsyne thingy. That's actually probably something that we did very well. Because we started RavenDB as ACID by default, and there are actually configuration options that you can use to say, oh, don't do async operation, don't do ACID work, skip the fsyne, those sort of things. They have never been exposed externally, and we have never found them to be of enough meaningful performance before the to worth mentioning that. What we did do was spend 10 plus years understanding the ways that we could respect the ACID properties while still giving you good performance. And I've written a lot about that. If you're interested, I can talk a little bit later about how it works, but the general idea is that I understand that IO is slow. Let's see if we can do IO outside of the critical path. Let's see if we can reduce the amount of IO and the complexity of it. Now, so here's a picture of beautiful flowers, and now here's a wonderful song. And a lot of the things that Jepsen found are things that are bugs, things that are obviously someone missed something. So let's talk about something a lot more interesting. Let's talk about the conceptual differences in the strategies that Raven and Mongo use to handle transactions. So here's the idea. We have Raven that is transaction from the start, safety and performance, but it's not safety then performance, that's it. You have to have the appropriate performance level. So we iterate over that, and every single release got better. Mongo has been non-transactional almost the whole time. And while it eventually added transactions, they are with defaults, they are not really doing that much. So that's actually really interesting because of the impact it has on the system design and the pressure that you have on the system. If you have a lot of pressure, or if transactions are slow, I have to fix them. I have to find interesting workarounds in order to make sure that the system is speedy versus, oh, this is a configuration option that only paranoid users will use and they don't care about performance anyway. Let's go and build something else. Who wants to do the boring hard work? Now, here is some code. Now, I want you to tell me, how many times do you think we are going to have to go to the database in this code? This is us doing a transaction to update an account using Mongo. Let's look at the network calls. So start the database is a network call. Update one, network call, and commit transaction. So in order to manage this relative retrieval operation, I have to make 4 calls to the database. Now, what happens if each call to the database is, let's say, 15 milliseconds? Then I'm going to spend 60 milliseconds just on the network. Now, let's see why this matters. See here,
This is what happens behind the scene. Everything that you do in Mongo goes into the ops log, and then things are working on top of that. Now, what happens if I have two transactions? And I have someone who is trying to update this document. So this client is trying to update this document, and it's going to be blocked. And it's going to be blocked for quite a while, because now we are waiting for something to happen, for the next command to come. And it will come in another 50 milliseconds. It will come in 15 seconds or a minute. And that means that the internals of Mongo needs to do a lot more work. They need to be able to handle locks and deadlocks and a whole bunch of other stuff like that that drive a lot of complexity now. There is a great paper that tests the relative cost of operations inside databases. In this case, they're talking about OLTP databases, relational databases. And in this paper, they found that about 40 to 60% of the time in a database was spent on logs and logs management. Over half the performance of the system is around stuff like that, which is insane. Now, everything that we have talked about so far was when we are talking about a single database. What happens when you run in a cluster? In a cluster, every time that you do something like this, you need to have a majority. So you have 3 nodes in the cluster, and I do a start transaction. I notify B that the transaction has been started, as well as C. I get confirmation from B. Now I have a majority. 2 out of the 3 confirmed, so I can immediately reply to the client. Afterwards, C can notify us about it. And again, make a change, notify these 2, and you understand how it goes. 4 round trips from the client to the server. Server has to do another 4 round trips. So 1 for each one of those, and effectively twice the amount of operations in total. I'm saying that it has to have half of that. It has to replicate it to at least one other node in the cluster. And the thing that is really annoying, who know how many fsynes are actually required? That depends on way too many things, and at worst, it may mean that you have a lot. An fsync here to send a command, fsync here to confirm that you accepted that, and then fsync here to make sure that I acknowledge that I got the notification from A, etc. So that's something that is not so good from our perspective. And I really love this. Whenever I teach or whenever I talk to people, I keep bringing the fallacies of distributed computing. They are there and they are real, and people keep falling into the same traps. In particular, latency is 0 because I have 4 round trips. 50 milliseconds, 50 milliseconds, 50 milliseconds, 50 milliseconds. That's a lot of time that I'm wasting. Let's look at the same thing in Raven. And you can see that we don't have to open an explicit transaction. We're doing something interesting here. We're saying, okay, give me both the form and the to in one call to the database and give that to me as a dictionary, get them out, do whatever logic you need to do, and save changes. Now, here are the network operations that are going to happen. We have 2 of them. It's just a single fsync. Let's see how it works. It works by saying, okay, first from the client to the server, load these 2, and you get it back. Everything else that we do, we're doing in memory. we modify form 2 and create a new transfer document, then we call save changes. And we write it, we're successful, we're done. Now, what about transactions? Where is my transaction? Here's the transaction. This is where I saved all of the data in one shot to the database. I don't have to do multiple calls. And because I don't have to do multiple calls, because a single route trip is enough, it means that I have a huge opportunity to optimize things. And RavenDB is taking full advantage of that and is able to do things much more nicely from the point of view of the system. Now, let's look at what happened when RavenDB is running in a cluster. Now, I'm saying, okay, I don't need just a session. I need a session whose transaction mode is cluster-wide. And now, instead of using just documents, I'm using the compare exchange value. And this is a database-wide operation that makes sure that we can do distributed atomic operations, compare exchange operations. And same thing going here, then concept changes. And that's pretty much about it. That's how it was. That's how it works. Notice that even so, the read didn't have to go anywhere. So even in the worst case scenario from our perspective, we only had to do one cluster round trip, not multiple of them. Now, one of the reasons that we have such different models of behavior is about what we expect users to do with the software. The typical system for database interaction has been created in the 70s. We have big databases and they were on this massively expensive hardware and you run one application custom. There was almost no concurrency, or if it was minuscule. But today, the situation is very different. We are working with stateless systems. If you're looking at your system and you're running and you see how we're actually working with things, then I'm not opening a connection to the server and keep sending commands. Instead, I'm doing interaction, show the result, and then at some arbitrary late time, another interaction, and show the results. Now, this is the model that we have here. Get the results, do the load form, give me the HTML, wait and do whatever you want, and then come back. Now, here are the results that I want. I'm going to call save changes with optimistic concurrency and get out. By the way, I haven't mentioned that. This thing is set up to do optimistic concurrency because of compare exchange. And this thing is set up to do optimistic concurrency because we have explicitly set this value. What this means is that the operation as a whole will fail if any of those was modified behind our back. And that's much how we're actually working in the web. Render a page, let the user decide how to do that, and then act upon that information. In many cases, you need to act on the information that was correct when the user last saw it. And with RavenDB, that's just easy. Okay, now is the time for questions. And I hope you prepare some because I have a lot of material to go through to be this talk, and I'm trying to figure out what would be the appropriate level to give you information. I didn't want to start giving you, oh, here is the bottom of the stack. This is how we read bits from disk and stuff like that. You can use the QA button at the bottom of the screen to ask questions. In the meantime, I'm looking at the poll results, and if you have any additional, if you haven't answered the poll, please do so now. The polling result is really interesting. There are quite a few here who think that the primary thing that we should do is do more work to market RavenDB, to give more information about what it's supposed to do. And all of you think that being transactional is important. That's good. While we're waiting for questions, I want to remind you that we recently released 5.0 in beta, RavenDB 5.0. We are currently at feature freeze, and you can get the latest nightly builds and test them out yourself, either directly on your system or in the cloud. We are really looking for feedback from people to put the new version on the spot and see how it behaves. Some of the new features in 5.0 are the time series, where we have the ability to store a lot of data that change over time. And what is probably going to be really interesting in the cloud is the document compression. And RavenDB has a really smart way of compressing data, compressing documents on the fly. And we have tested it out, and it can saves you about 50%, slightly higher than 50% on average, of the size of your data. If you're running in the cloud, that means that your cloud storage bill just got cut by half. That's something that is really interesting. If you're using IoT, then time series is certainly something that I would like you to pay attention to and provide us with some feedback. And that's it. Questions? Yes. Sorry for asking. How are rollback and undo different between RavenDB and Mongo? That's actually a really interesting question. The way that okay, let's talk about this. With Raven, you have an optimistic operation. So Sajiv is asking, I'm sorry, I forgot to mention that. How are rollback and undo are different between Raven and Mongo? And Sajiv is saying, sorry for asking, please do. I actually budgeted time for questions because I have much better time answering questions than reiterating what is on the presentation. So here we have a transaction. This transaction may fail if either one of these documents has been changed. So we send that data to Raven, and here we start processing that. And if there is a failure in the transaction, we simply abort it. So we start running the transaction. We start modify. We have to modify the form. It hasn't been changed behind its back, so we're good. Then we have 2, and 2 was changed. So we have to roll things back. Now, at this point, we have modified a copy of the data. So the way RavenDB works at this level is that we use something called cow, copy on write. We clone the data that we want to modify and put it on the side, modify that on the side, and only on commit will we actually go ahead and make this public to the world. RavenDB uses snapshot isolation by default, and transactions are effectively going to observe serializable behavior between operations that happen on the same node. So what this means effectively is that RavenDB can just, let's free this memory, and that transaction is done. And if you want to do to commit, okay, let's take this memory and throw it to disk. If you with Mongo, they're using a storage engine called WireTiger, and that uses a more traditional. I think they use a variant of the RES algorithm for journaling processes. And what happened is that they're modifying data, but at the transaction rollback, they have to go in and do a lot of stuff. And they're able to do this undo by looking at the journal. And just the logs that you need to maintain and reduce is one such example. If you really care, this is not RavenDB code. I want to emphasize that. But here is an example of committing. You iterate over a list of modified pages in transaction, and then you write it to disk. Again, not RavenDB code, this is just something that we play with. Matthias is asking, data transaction cover everything that Raven can do? Time series, counters, attachments. Can I set everything in one transaction? Yes, and documents, attachments, counter, revisions, time series. There's another thing that I'm missing that revisions, attachments, documents, counters, time series. I can't recall, but yes, the short answer is that everything in RavenDB is going to fit in this model, and you can have a single operation that will mutate a counter, append an item to a time series, add an attachment, and delete a document. All of them are going to be run in a single atomic transaction. We actually never consider not allowing that to be the case. As I said, transactions are just something that you do. That's not something that you have to ask for. Okay. Any additional questions? Going once. Going twice. Guys, thank you very much for showing up for this webinar. I hope that you enjoyed learning about the differences between Raven and Mongo, at least with regards to how they do ACID transactions. My next webinar is going to be about indexing, but not how indexing works or those sort of things, but practical realities. Oh, I want to use an index to solve these sort of issues. Let me show you how. Feel free, and I actually would really love it if you could send us an email. Here is this or that scenario that I want to try out, and I'll be very happy to discuss this in the next webinar. Thank you and goodbye.